Hey everyone, it's really great to be here in Berlin. It's my first time on DroidCon Berlin, and I'm looking forward to meet a lot of new people, familiar people, someone I already know here. So don't hesitate to come and say hi. I'm here for like all 3 days. I'm working on Kotlin and Android infrastructure at Meta for like almost 4 years now. Prior to this, I spent a lot of time optimizing server-side JVM-based applications for Alibaba and other companies. I'm really passionate about making the developer experience better, allowing developers to ship their code safely, reliable way, deliver it to users so they don't complain at all. So that's all about me. In the past few years, I'm trying to understand the world of build systems and the ways to make Kotlin and Android builds faster. So my talk will be about build system, making compiler faster, and so on. And the story of the talk starts in 2019, when a company named at that time Facebook had a very limited amount of Kotlin code. It was not the language of choice for Android yet. At that time, we happily shipped Java to our users in applications, and our mobile clients worked well. However, we had a number of reliability issues. We had a null pointer hell, a lot of crashes, and so on. In 2022, almost 10 months ago, I think, it was October, we shared a number of lessons learned from our high-scale combined manual and automated conversions from almost 0 lines of code to 10 million at that time. Now, this number is probably significantly higher. So a lot of problems I will be talking about it, they happen at scale. However, I try to structure the talk in the way so even smaller apps, something you can ship to the store within months probably, they could also benefit from the information you're going to get today. I also try to formalize and structure some types of builds and the way to approach the optimization there. Build problems were not the only ones. So we had the issues with ID, the issues with like linting infrastructure, and many more things that happen at scale. So if you're interested to get more understanding of the other aspects of the significantly growing Kotlin code base, you can go to YouTube and check one of my previous DroidCon talks, probably DroidCon London or New York. OK. Engineering is all about trade-offs. I think there is no need to explain this to the audience we have today here. Most of our technical and design decisions solve a problem, a concrete problem, the one we have at the moment. On the other side, they generate other problems to ensure we have a job in a few years. In our case, we were not happy with Java for many reasons. But the major one is that the developer velocity and the velocity of our changes reaching production was not enough. And the quality of code was far away from what we wanted to have. And the other opportunities on the table, like null safety guardians through static analysis, for example, were not as mature at the moment or simply didn't work for all the cases. So our developers complain about Java. We aggressively converted to Kotlin. We degraded the build speed, and as a result, our developers started complaining about Kotlin. So it's quite an interesting loop. But before we will get further, let me ask the audience, like how many of you are happy with your Kotlin Android build speed or build times for your apps? Okay, it's significantly more than over the previous conference when I asked this. So I saw at least 15 hands here. So in fact, the length of the stock is probably enough to compile a medium-sized Kotlin application, which is fine, I guess. But we always want to deliver things faster, ship faster, build faster, iterate on things. To understand why we degrade the build speed, it's important to get some history lesson. So, as it always happens, we are playing against the optimizations we had before, so-called old money. Previous generation of platforms, and engineers invested in these generational platforms. Previous generation language, like a lot of years of engineering were spent to make Java compiler where we see it today, so like over 20. And all these approaches that perfectly work now or before, at some point we realize they don't scale further, and at this time it will be a certain degradation in the quality of life, quality of development, or you name it. So whenever we speak of Java versus Kotlin, it's like the build graph optimization that Java has, build system like Gradle or Bach have, or the Java compiler, which is like by design significantly fast because it doesn't have this amount of synthetic sugar. It has the type system that is easier to process, and so on. And we even don't expect Kotlin compiler to be at any time on par with Java. We don't. Probably JetBrains has a different take here. Let's try to categorize the builds we are doing on a daily basis here and try to understand what are the approaches that we can apply for some of these categories at least. And the surprise is the meaning of a quick build is quite different for all these categories. A clean build is something that you want to do with your application whenever you just checked out the code. Let's say you don't have the internet connection, so you cannot use any caches. You just do a cold build, or probably it's even in CI. You likely need to iterate over everything that works for your application. A single target is the change that you probably did in one module that doesn't affect anything else. So single build is quite important when you iterate not at the level of the application, but at the level of a single target. So you either need to run unit tests for these targets, or you need to use some sort of inspection there that you just need the jar of this concrete module. And there is another thing, the incremental builds. Incremental builds is when you don't have a cold machine any longer, like for the cold builds, you already try to build some stuff. So your cache is not empty, it has something. Then you modified a few things, probably in several modules, and you try to build your application. And here your goal is to build a few modules and the transitive dependency of these modules, and then the transitive dependency of that modules. So the quick build is the one that rebuilds less things over this build graph. But let's be practical today. So we are going to build a specific app. It's called the app now, so for simplicity. It contains some native code, some something we inherited from Java, called Java Heritage, but it's mainly written in Kotlin. So Kotlin things are blue, and non-Kotlin are not blue. Your concrete build, your app, really and heavily depends on what exactly you have in this build graph. What is the distribution in between native, Kotlin, Java, whatever else you have, what dependencies you have. Like in the modern day, you can, with Kotlin multi-platform, you can have even dependencies on iOS here, whatever, like your choice. If you want to make your builds slower, use whatever. Another thing that matters is the size of your nodes. Is like if they are quite big, then the complexity of the compiler work for this concrete node is probably higher than to smaller things. And the transitive dependencies, as I mentioned before, they might be different. And finally, your build setup, what build system you use, how well it's optimized, and many other aspects. Let's first talk about the compiler throughput. I mentioned it briefly, but to understand the impact of the various compiler throughput optimization, let's imagine we are building the app within a single dedicated process, like the Gradle daemon or the Kotlin daemon working, or like maybe we even have just one thread of the executor that is on our local machine. In this case, we can flatten the build graph into some sequence. We can work with this. It's like it's a queue with some priority, and the priority is the actually dependency in the build graph. So this queue, in our case, is on the right of this slide. And now compiler throughput is a compiler optimization that is applicable to a single compilation unit. In our case, it's Kotlin C, Kotlin compiler invocation. There are obviously compiler optimizations like throughput for native code compilers and for Java, but we are not talking about them today. So it's quite easy to imagine a compiler throughput optimization as follows. Let's say we are not happy with the binary size of whatever we are compiling for Android. So our APK is big. Probably it's big because of the resources that we are shipping with the application. But let's say resources are quite well optimized. Now the problem is the amount of code we are shipping, the amount of DEX code there in the APK. And let's imagine we are not happy about this, so we introduce some sort of the post-processing in the Kotlin compiler that deduplicates some of the fields, some of the strings, or something else. Yeah, sure, it saved the APK size, but as a trade-off, we are spending time on this optimization before we ship it to like end users by doing this deduplication. So in this case, the compiler throughput optimization would be to roll back this optimization. And just in case, in Kotlin compiler, there is a thing called the backend IR optimizations, and it's possible to turn them off. So in this case, you probably will get some boost in the throughput. However, the result is unpredictable, so I cannot suggest it to anyone, but this is something you can try if you want. So in our case, let's imagine we somehow shrunk the Kotlin targets and got this nice boost. Let's also try to classify the build optimizations today. So compiler throughput is a universal one. It impacts the single target builds, like the clean and incremental. If we need to like rebuild for incremental, anything Kotlin related, or if for clean build, because basically all the build contains of some nodes of Kotlin invocation. So it should help everything. With this in mind, it's like not surprising that why JetBrains is investing in the build speed improvement by improving the compiler itself. But what are the other options that we have on a plate and what we can use as developers? So a few quite obvious answers. The K2, a new Kotlin compiler. The migration to the newest Kotlin compiler versions, like something on top of 1.6. A quite interesting thing is the KAPT deprecation and the move to the Kotlin symbol processor instead of whatever is widely used now. And another one here that I listed, there are quite many more, is the Kotlin parallel backend compilation, which was the experimental feature at the time when I created the slides. Let's start with K2. So let's have a look. An average compiler, the industry-level compiler, is quite a complicated creature these days. So Kotlin contains a front-end, a back-end stage of the compilation or compiler, and let me call it everything else that is not very important for this talk. So let's focus on front-end and back-end. A while ago, the backend migration to intermediate representation, so-called IR, happened. From my understanding, it didn't bring any improvement in the build speed. However, it simplified the way the compiler is written. Nowadays, something called as K2 is effectively a rewrite of the front end of the compiler to something called the front-end IR or FIR. For our cases, for our code base, the front end was always the thing that slowed us down. So it's not surprising that we are investing in trying to build the application using K2 even now, when it's probably not in beta stage yet. Let's now try to apply the K2 to the build that we are doing. So for simplicity, we still have this single process machine. We have the queue of tasks and only one worker. Let's split each Kotlin target into front-end and back-end. Now, and regroup them. So the something green on this slide is whatever we run backend, the time we run backend for, and front-end is red. So the K2 will minimize the time we are spending running front-end. And as a result, the compilation changes quite significantly in this model. After grouping, it's like quite easy to see how it happens. However, I understand for general usage, K2 will be probably available in 2024 or late 2023. Depends on the cadence of release, but it's coming in Kotlin 2.0, which I'm quite excited to see soon. Okay, so Kotlin K2 is quite far away, Kotlin 2.0. What can we do if we need some throughput improvements today? The easiest option probably would be to migrate to something, some later state, the version of the compiler later than 1.7. Because 1.6.21 to 1.7 was quite an interesting performance bump that we were able to see even for our builds. Even with them fluctuating quite a lot. I cannot share numbers, but I'm here sharing the one that JetBrains used in their test tracker, so the link is on this slide if you want to check more. So this is something you can do even today. And from my understanding, the way how the industry upgrades the Kotlin version is there are two opposite positions on different sides of the spectrum. The one that the applications where it's super easy to just bump the version, and the others where it takes like probably weeks to have even the minor updates. For some reason, I didn't see anything in the middle, so it's quite interesting. But if you are not yet on Kotlin 1.7, this is something you can try. Key 2 is expected to go better in beta stage soon, with a promising impact, as I mentioned. So it's probably 2x based on the data that JetBrains shared, and as a second source of truth, during the Google I/O recently, they shared the similar numbers, or even the same, if I recall correctly. However, going to better is slightly complicated for some of the apps, as KPT support is something important, but as of today, I don't see it properly supported in these stable versions. Another opportunity is migrating to the Kotlin symbol processing, which is the tool that is provided by Google, and we expect it to become the default standard for anything like the annotation processor in the past era. So if you don't need to modify the existing code, I strongly encourage you to work with Kotlin symbol processor as a better alternative for KPT. And don't use KPT at all. For like, I didn't see a build system where KPT works well. And the last thing I want to mention about improving the compiler throughput, that disclaimer didn't work for us, but probably because we use a heavy parallelism at our targets. So it might work for Gradle builds. It might work if you use something non-conventional as a build system. So Kotlin parallel backend is something where you can parallelize the compilation for within a single target, the compilation of some intermediate representation on the backend. JetBrains claims that there are some improvements on their benchmark depending on the number of threads that you're using or processes. Try it out. It's interesting to see if it could help anyone. But let's get to more to the build system side of the story, and let's discuss the other option that we have on the table. So parallel graph execution is something when you no longer have just one worker, as we used before for examples, but you have some of them, many. In this case, it's possible to build a parallelism. So it's possible to allocate the resources, the workers, in the way that they build part of the build or part of your nodes in the build graph. But you need to make it smart, so your workers don't wait for their dependencies whenever they need some, or they have some shared resources, let's say, in the file system. So there are a few solutions in the build system, the existing build system that you can use as of today. There are various options how to run this parallelism. So for example, you can run multiple Kotlin daemon processes, or you can even run a few targets in the single daemon based on some rules. There are other options as well. But a fundamentally significant problem here is the critical path. The critical path is something that you just simply cannot parallelize as a part of your build. In this case is the path from app to bar to foo to util to IO lib. I allocated it to 2 workers just to make sure we understand that it's not necessary to build the full critical path, the full number of critical path instances at 1 worker, but usually, sometimes we do build it on the 1 worker. And yeah, minimization of the critical path is something that developers could do to make the build system faster. There are multiple ways. Like one of the example is to flatten the dependencies somehow, probably splitting the modules or just removing unnecessary dependencies that we are transitively adding to the build or build scripts. There are a few tools that are open source or even like a part of the build system, like health checks, which could help you identify. If you don't have the critical path checker as a part of the project, it's not that complicated to set up one. And so we are adding the critical path and parallelism to the build optimization classification. And in this case, we have, they don't impact the single target for like obvious reason, because they impact the build graph, but they still impact the clean build and incremental, which is good, right? Distributed build graph systems. Then the next level of improvement is to include the remote execution technique to your build system, or like alternatively, the remotely or distributed cache of your targets. So what we have here is we have like 2 local workers and we have a few remote ones. And remote one, you configure how the remote workers operate. They might be very tiny CI machines, like with a few gigs of RAM. So in this case, you free a lot of things from your local machine, because like whenever you build Android application, MacBook can get like really on fire, and like not easy to even run browser in this case. So, but what you need to know about the cost of the remote execution, then you have to transfer data to the remote machine or remote worker and back then, or maintain somehow the distributed cache. I don't know how to do this. There are multiple solutions. And for example, the BART 2, the recent build system open source by Meta, uses this technique. But there are other, not trying to sell it, there are other options in the industry. So yeah, let's put the remote execution here. So I really don't know if it makes sense to build a single target, the one that you hear mostly about on the remote execution, because it's transfer of the data back and forth. But for clean builds and incremental build, the spread of the load is definitely what you should consider, depending on the app size. Okay, takeaways so far. Minimize or try to minimize a critical path in your app. Try K2 if it's an option. Deprecate KAPT. Don't use it for the new annotation processors. And try distributed builds or distributed caches if it's an option. OK, then getting back to the title of this talk, so using the ABI to improve the builds. Now we are getting to the area where we can declare that the best build is the one that didn't even happen. And we'll try to understand how to use ABI to reduce them. ABI, or the application binary interface, is like whatever public you have in the application. Let's say it's C-style headers, if you know what is C-style headers, or just everything that could be used as part of the API for your app. How a regular build system uses this ABI, or like how we match the caches if something is built based on what we saw before and we can reuse the cache. Let's try to understand it. So we have a module, and we somehow get the full hash of this module. There are various options. For example, when you have module, it consists of sources, resources, then some config, then a build system configuration, whatever. And then you need to transform it into a hash that you then can compare to anything. And later, if you compare it and you get the equivalent hashes, then you can say, yeah, I already built this, everything is good. Usually this thing is named the rule key or something like a rule hash or whatever. For example, what doesn't impact the rule key and what does? If you change the source code, somehow the rule key is invalidated. So there's obviously nothing you have in your build system that you can use as a cache. However, if you change the garbage collector that you're using for the Kotlin daemon where you run the compiler, it probably doesn't invalidate the cache. So yeah, instead of building the full hash of something, you can build the ABI and then build a full hash of this ABI. In this case, the ABI is obviously smaller as it's a part of the public API only. And in this case, there's more chance that you will hit the cache and you will not need to rebuild stuff if you didn't modify anything. But back to the topic, what is ABI? So for example, we have some class foo, and I promise this is the only code written in Java. And then we'll try to build the ABI from this. As I said, we don't need anything private or any sort of implementation to get the ABI. So we just naively strip everything from the class file that we're generating, or even the source file. A concise definition of foo. It still has type, it has still modifiers, it will have annotations because they matter, and it has the method declaration. There are various ways to generate ABIs, and depending on the one you're using, you modify the build graph. We are working on 3 of them. The class ABI is the simplest. Let's build the target, then first build target dependencies, then build the target itself, and then we'll strip anything that we don't care about, like on the previous example. Another case is source ABI, which is slightly more complicated. Let's build the target dependencies. Then generate everything that we need. In this case, we do not need to pass this stripping stage. So it should be faster. But it's like a throughput optimization instead of the build graph optimization. And the more powerful one is the source-only ABI generation. In this case, we do not build the dependencies, but instead we are trying to guess them or make stubs for these dependencies instead of building. It's quite a complicated heuristic, and it's not possible to cover the whole complexity of Kotlin programming language with this. But it works sometimes, and with the good benefit on the build graph. Yeah, and then after we guess everything, we just need to run a compiler frontend as in the previous case. Let's try to understand a few complexities that Kotlin brings us about with the ABI generation. And probably just the easiest feature in the language, or at least probably the most powerful from my point of view, is the nullability and the nulls as a part of the build system. So let's imagine we have a bar, and it's either nullable or a non-nullable field. And here is how this is interpreted in the class file. So we have a nullable annotations, or non-null annotation. But on top of this, we have a part of the metadata, Kotlin metadata, that changes when we change the nullability. So it's not possible to naively strip things, because you will still have things in the metadata that you cannot strip by just removing lines of code or lines of or bytes in the class file. So we need some better way instead of just stripping. And this is obviously not the only Kotlin feature that is impacted by this. Another one is the inline functions. So inline function is quite the powerful thing that allows us to write refire generics, allows to optimize things a lot. However, it comes with a cost. So in bytecode, like what we have is the full definition with a lot of methods. And the interesting thing is we need to take the inline function fully into the ABI, just because it might be used elsewhere as a part of the public API, and we'll need to reuse it after. So we keep it. Another thing is the private members as well. So like we have foobar, they are all private, but the problem is that they are coming into the Kotlin metadata as well. So we need a non-naive stripping that can effectively remove whatever didn't change, whatever is private but changed from the ABI. So in this case, we need to build something like a ABI class builder. It existed before in the Kotlin code base. It's no longer there, but it's here just as an example. So in this case, we need a visitor for all methods, all fields, or all classes. And whenever we visit something, we check if it's private, inline, static, or something else. And depending on this, we either take it to the build or we pass. So yeah, we have this build target. Again, it's a bit more simplified than before. And what we are doing, we are adding the ABI stages in between our Kotlin targets. But now, whenever we hit the cache hit or cache miss, we either move further or we stop there and stop rebuilding something in an incremental compilation. So if util just slightly changed, then the util ABI will be fine. And compared to the previous case, we even will not start building the foo. I already mentioned that the Kotlin compilation consists of the compiler frontend and backend, and it's possible to extract the ABI right after the compiler frontend stage. In this case, we just pass on the backend compilation and the full jar generation. However, instead of just passing, it's possible to move them to the separate parallel work streams. And in this case, we'll be able at the same time to generate the foo and foo ABI, let's say. And in this case, the parallelism increase. And you can try to color this graph, again, as I did, into different types of workers of how to distribute it in a parallel way. And finally, the source-only ABI. Imagine that instead of building something, we are guessing dependencies. In this case, if we are able to guess dependencies for almost everything, let's try to guess them for everything. In this case, we can start building the ABI for almost all Kotlin targets at the same time. Like if you have a good parallelism for the build, we can start building them all at once. This is something partly working for bug 1 and bug 2, so it's possible to check the code base. But how the guessing happens? Let's say we have an import of the user, and we have some creation of the user class. And in this case, we can guess that it is probably a class. So it should not be an interface, but it's probably a class. However, the things are getting more complicated if, let's say, we are importing a very important string, which is a literal here. However, we are assigning this important string to an integer, which obviously made this an integer if everything is correct. So we cannot sort of guess that it's a string, but we might do it by the declaration. So things are complicated. And the last but not the least kind of optimization is the use classes or dependency tracking. Imagine you have a module A and module B, and they depend on each other somehow. A depends on B, so we should compile B first. However, we only use apples from the classes declared in B. In this case, it's possible to ask the build system somehow to guess the dependencies and split module B into 3 targets with apples, with oranges, and with banana instead of whatever we had before. So we are filling in the gaps in our build optimization classification by adding the compilation avoidance here. And compilation avoidance, again, will not improve your single target, because it's a build graph or build system level optimization. It will impact the clean build and incremental build. If your build system supports building against ABIs, try it. It might save a lot of resources. And finally, here is the number of references to whatever I was talking about here. In Kotlin, Gradle, Bug1 and Bug2 build systems. And as a takeaways, we have a few things to optimize your build tree, like compile against ABIs, minimize the critical paths, try to use the caching or remote worker solution, and everything I said before about the Kotlin compiler optimization to make it faster, either K2 or KSP. Thanks a lot. That's it.